For Chapter 23 for AP Physics 2. There are a lot of the circuit homework. I may go over some things other than that. But basically, the first three are conceptual questions. It gave you this graph. I really should put that below these. It's asking you to rank the resistances. So you can see that the potential difference or the voltage goes down for each of the three resistors. The slope is steepest for resistor 3. And since the current would be the same through this circuit, since it's a series circuit or a series part of a circuit, if V is greater, that means R is greater. So the steepest slope represents the biggest resistance. So that's why I have 3 is greater than 1 is greater than 2. For question 9, it's asking to rank the currents. And it says that there's 4 identical resistors. And in part A, it's asking you to rate the potential differences. So A to B would equal the potential difference of C to D. And the reason for that is all the battery's potential is used up, they put in air quotes, or converted from electrical potential energy to heat and light between those points. So it both has the full potential difference of the battery. This current I1 is greater than I2, which equals I3. Current's the same everywhere in a series circuit, but is not identical in all series circuits. So in this particular case, we've got only one resistor, so the voltage divided by that resistance gives us more current than that same voltage divided by 3 times that amount of resistance. For question 36, this is actually a pretty cool thing to think about. So normally when we hook things up in our homes, everything is hooked up in parallel, so it gets a full 120 volts of potential difference. And that means that the voltage is the same for all of them. And so that voltage divided by the resistance of that branch gives us the current through that branch. So if we have something with lower resistance, it would have higher current. It would end up being a brighter bulb because you have the same voltage, 120 volts, but now you're dividing it by, or you're multiplying it by a higher current. So in this particular case then, I want to think about the fact that the lower wattage bulb actually has more resistance. So I can do that by thinking about it in a parallel circuit. I would have 120 volts squared divided by the power, which is 40 watts, would give me my resistance. So P equals V squared over R. Oh no, oh yeah it is, because P equals V times I, P equals I squared times R, P equals V squared over R. So I can indirectly figure out the resistance of these. So the 60 watt bulb has less resistance. Again, it kind of makes sense in a parallel circuit. A 60 watt bulb is brighter than a 40 watt bulb. Okay, and so those are things that now we put those two bulbs, the 40 and the 60 in series with each other. They're having to share the 120 volts, and so the bulb with the greater resistance actually ends up getting more voltage because the current is the same in a series circuit. And V equals I times R. So if we have the same current and the 40 watt bulb has a greater resistance, it would get more voltage. So actually the 40 volt bulb would be brighter. That's a pretty cool thing to think about. For the problems, problem 9 gave you this graph, and it's asking you to draw the circuit starting from the lower left-hand corner. So initially we're at 2 volts of potential. We go down to 0. So that says if we're decreasing, we're going through a resistor. Then we bump up to 6, so that says you're going through the power source, and it goes down to 4 again, so we're going through another resistor. This resistor has to be half the resistance of this one because the potential difference is half the change of this one. It told us there were 2 amps in the current in the circuit, so I know that the total resistance of the circuit is 3 ohms. 6 volts divided by 3 ohms gives me 2 amps. So I can predict this is a 1 ohm resistor, this is a 2 ohm resistor. That actually goes beyond what was being asked. It says you have 3 1 kilo ohm or 1,000 ohm resistors. Put them in as many arrangements as possible to get as many different resistances as possible. So I did that here. I had 4. 3 in series gives me 3,000 ohms. 3 in parallel gives me 333 ohms. 1 in series with 2 in parallel give me a 1,500 ohm total resistance. And then if we have a parallel circuit, but 2 are in one branch and 1 is in the other, this becomes a 2,000 ohm branch. That's a 1,000 ohm branch. And that becomes 667 ohms. For problem 22, it's asking you to figure out the current through this resistor. So there's a couple ways to do this. I know since these power supplies are pointing the same direction, I would add the voltage. So that gives me 7.5 volts. And I know that I'm using 2 volts here, 3.5 volts here. So I've got 7.5 volts. I use 5.5 volts up. That means I have 2 volts left to use up across this resistor. So then I simply use Ohm's law. I equals delta V, potential difference divided by R, 2 volts over 150 ohms, and that gives me the current. That would be the current through all these resistors, by the way, and through the batteries. Going to problem 30, I did a lot of different drawings on this. So it says find the current in the circuit or through the battery. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 resistors, and I just attack it one at a time. This 10 and 2 are in series with each other, that becomes a 12. Now that equivalent 12 is in parallel with a 6. If I add that using the rules for parallel resistance, that becomes a 4. Now that 4 and this 8 down here, which was this in the previous diagram, become 12 because they're in series with each other. Now that 12 and this 6 are in parallel, so that becomes a 4. Now that 4, which I've put in orange, and this 4, which was initially down here, are in series, and so that becomes an 8. So now I've got an 8 and 8, and they're in parallel with each other, and that becomes a 4. I've got this 6 and this 4, so the 6 was initially up top here, are now in series with each other, that becomes a 10. So I end up with a circuit that has an 8 ohm resistance in parallel with the equivalent of a 10 ohm resistance. And that becomes 4.44 ohms. And so now I do Ohm's law, 6 volts divided by that total resistance, and that gets me 1.35 amps. So look at the PDF if you have questions, but I did this one step at a time. It's hard to do it other ways. I mean, you might be able to do 2 steps at a time, like say, hey, I can do 10 plus 2 is 12 in my head, and then do that. 1/12 plus 1/6 gives me 4. If we flip it. Okay, this one was sneaky. We may go over this in class. So current here going to the right, current from 3 to 2 going to the left, current from 3 to 4 going to the right. This is a very sneaky circuit. So the way that you want to think about it is tracing paths. So you've got 10 volts over here, 0 volts over here. There's no resistor between the 10 volts and the 1, and so that's got to be at 10 volts. There's no resistance between the 1 and the 3 because it's a short circuit, so that actually has to be also 10 volts of potential difference at 3. If I look, 4 is at 0 volts because it's basically touching the 0 volt thing, and 2 is also at 0 volts because it's a short circuit from 2 to 4. So I've got 10 volts, 10 volts, 0 volts, 10 volts, 0 volts, 0 volts. So that helps me think about it. So if I think about this, it's asking about the current flowing through each resistor. So here, I am going to have 10 volts at this point, 0 volts at this point. 10 divided by 10 ohms is 1 amp, and that's flowing to the right. Here at 3, I've got 10 volts, 2, I've got 0 volts, 10 ohms in between. That's 1 amp flowing to the left because 3 is at a higher potential than 2. Here I've got 0 volts at 4, 10 volts at 3, 10 divided by 10 ohms is 1 amp. 3 is at a higher potential, so the current's flowing to the right. When we think about wires, the wires, certain of those wires actually have 2 amps going through them. So for example, from 1 to 2 directly would have 1 amp, but this has got to carry 2 amps because it's now going to split and have 1 amp go from 3 to 2 and 1 amp go from 3 to 4. The same way this wire would now have 2 amps because it has an amp coming into it as the current goes from 3 to 2 and has 1 amp coming into it as the current goes from 1 to 2. So these really deal with the junction rules. And honestly, if you look at it carefully, it basically comes down to a parallel circuit, which is annoying because it certainly doesn't look like that up here. Yeah, I had to really think about visualizing that as that parallel circuit. I've kind of like swapped and moved this up. It would be like if there was a computer simulation to do that, it'd be really cool. For number 72, that's the last problem. I had this circuit here. I had two 24 ohm resistors, so in my answers down below, I noted this one with a purple asterisk, this one with a black dot. So the first thing I'm going to do is simplify this circuit. These two become a 6 ohm resistor, 6 ohms in series with 6 ohms, that becomes 12 ohms. 12 ohms in this middle branch, 24 ohms in the outer branch, that becomes an equivalent 8 ohm resistor. So my simplified drawing looks like this. I've got 4 ohms up top and 8 ohms for all this mess on the right side. So the total resistance of the circuit is 12 ohms. The total current for the circuit, 24 volts divided by 12 ohms, is 2 amps. So the 4 ohm resistor is all by itself, so I did that work first. I knew that there was 2 amps going through it. It's 4 ohms, that's 8 volts. At this particular point, you could have basically realized that this was the total current in the circuit, so 24 volts total divided by 12 ohms total gives me 2 amps, and all that is going through 4. The second one I did was this 24 ohm resistor because it's all by itself. So the way I thought about it is I used this particular version of the circuit. So I knew I had 2 amps, and this whole mess here is equivalent of 8 ohms. In this whole mess here, this 24 ohm resistor is the only resistance in this outer path. So I know that the outer path is going to have the same resistance as this inner path, and I know overall there's nothing else using voltage in that outer path. So I simply use this diagram and I say 2 amps total is going through an equivalent 8 ohm resistor. That ends up giving me 16 volts. You could also have said that if we had 8 volts here and we have 24 volts total, 24 volts minus 8 volts used at the 4 ohm resistor would give me 16 volts left to use at the 24 ohm resistor. Either way, when you get this, 16 volts divided by 24 ohms, which is the voltage and resistance of that path, gives me 0.67 amps. So then the third thing I did was this 6 ohm resistor all by itself. So I thought about this branch. So this branch has 12 ohms total. All the current going through this middle branch has to go through this 6 ohm resistor. So to find that current, I'm going to take the voltage across this whole branch, which we just said was 16 volts, and we're going to divide it by the current of that branch, which is 12 ohms, and that gets me 1.33 amps. The other way you could have thought about it is you have a total of 2 amps in the circuit. We just found out we had 0.67 amps going through here. So 2 minus 0.67 gives me 1.33 amps through here. And now, if I know the current going through the 6 ohm resistor and I multiply it by that resistance, I can get 8 volts. The last ones I do are these two. There's a bunch of ways you could kind of figure this out. I showed 2 down here. If we treat this and think this is an equivalent 6 ohm resistor for these two, and we just found out we had 1.33 amps going through this part of the circuit, I could say 1.33 times 6 ohms equivalent, give me 8 volts. Or I could recognize that across this whole component, I have 16 volts potential difference. I already used up 8 volts here, so 16 minus 8 gives me the voltage across either of these, which would be 8 volts. So the current is going to be 8 volts divided by 8 ohms for this path, and 8 volts divided by 24 ohms for this. Notice that those two add up to 1.33 amps, which is the total we said we had going through the 6 ohm resistor. So it's a lot of logic and back and forth and zooming in and zooming out, but that's a really good Ohm's law problem.